Alright fellas, what we're looking to do here is provide a general proof for the locus of a parabola. And then we could do that numerically. So if I wanted to find the locus of points P, X, Y that are equidistant from the point A, and I'll call that the point 0, 2, and also the line Y equals negative 2. Now already in your mind you should be thinking, alright, well if I've got some fixed point here 0, 2, and I've got some down here, some line down here y equals negative 2, well we know that that's the focus, that's the directrix, and we've got a parabola. That's the locus of a parabola, but let's go prove that algebraically. And then what we'll do is remove these numbers and make them in a more general form, and then we'll go prove that x squared equals 408 is in fact the formula for any parabola for a fixed point and line. So what are we going to say here? Well, the distance between some point P, and I'm going to draw it up here in the first quadrant, it could be anywhere. Obviously it has a fixed set of parameters that it can go along, so it's not going to be down here in the third or fourth quadrant, but along this path it can go anywhere. So I'm going to pick some point there. We've got our distances there. Now they're not drawn to scale on my diagram, they're not perfect. Well, I hope what you see is that that distance there is actually perpendicular. Okay, so the distance from my point P to that, I'll call it PL, is always a perpendicular distance. Well, that's just the difference between y and negative 2. Well, that's just y plus 2 units. So that's y plus 2 all squared. Okay, and then of course my distance PA. Well, that time we've actually got to use our distance formula, so it'll be x minus 0 squared plus y minus 2 all squared. And of course those are both square rooted, but we know we're going to square them because the square of the distance will be equal, so what we'll end up with is y plus 2 all squared equals, well, x minus 0 squared is just x squared, plus y minus 2 all squared. Expand that one out, y squared plus 4y plus 4 equals x squared plus y squared minus 4y plus 4. Well, let's see what happens here. Well, these y squareds, they are equal on both sides, so can be removed. 4 and 4, well, they're equal also. I'm going to rearrange this now. What I end up with is 8y equals x squared, or in the more conventional form that we use, x squared equals 8y. Now, of course, that is a parabola with its vertex at the origin, its focus at, well, first we need our focal length. Now, our focal length here is 2, and so that means our focus is at 0, 2. And the directrix is at y equals negative 2. Well, of course, that's straight back up into here. That's back where we were originally. Okay, so that has just confirmed it. Now let's go do it, rather than numbers in there, let's go do it with some value that's more general. Alright, so I'm going to make my locus of P, again, x, y, as we always do. I'm going to pick my fixed point is going to be the point 0a. Now again, a is just some number, so a could in fact be positive or negative, it doesn't matter. And then I'm going to make the line that it equidistant from negative a. So essentially, what we're saying is we've got some fixed line that has a y coordinate that is consistent, and then some fixed point that has a set of coordinates 0a. So again, let's go find that distance. So I'm going to call that A, and that'll be my line as well. So my distance PA is what? X minus 0 all squared plus y minus A all squared. Again, that's the square root of that. We know what we're going to do though. The distance between my point and my line, again, the square root of, well, again, we know that that's going to be a straight vertical distance. The distance from my point down to my fixed line has to be at a right angle perpendicular to my fixed line y equals negative a. So it ends up being just y minus a all squared. And as we said in the last one, it was y plus 2 all squared in the last one, so it's y plus a all squared here. So what we end up with there is y plus a all squared equals x squared plus y minus a all squared. And of course I've squared both of those. Okay, if the distances are equal, the square of the distances is equal. So we end up with y squared plus 2a plus a squared equals x squared plus y squared minus 2a plus y plus a squared, and again the same sort of thing happens, y squareds, a squareds. If you ever end up with a locus that you think is a parabola and you end up with both x squareds and y squareds in there, have a look again, because you've ended up with a circle. But here what we end up with is, I've actually made an error here. Those should be, they're not just 2a's, they're 2ay's. Okay, because it's twice the product of that, y times a times 2. So what do I end up with here? I end up with 4ay equals x squared, or as we more conventionally write it, x squared equals 4ay. Now what we could do is we could go prove that this works for a parabola that doesn't have its vertex at the origin. So I would go pick some fixed point, say BA, and then what we'd end up with here is we'd end up with this B hanging around in here for both the X and the Y side once they're factored. So, but look, I'm happy if we can recognise that this is the general form of a parabola, x squared equals 4ay, given that we've got some fixed point A units above the origin and some line A units below the origin. Okay.